Hello everyone, welcome to the 7th week of Scalable Data Mining course. In this lecture, we are going to discuss the problem of finding similar items. So now, the goal in this case is to find near neighbors in high dimensional space. Now, what are near neighbors? We define near neighbors, points in high dimensional space which are a small distance apart. We will see a more formal definition later. Okay. Now here, one of the key things is this distance. Okay. What is a good definition of distance? Okay. So the notion of distance is dependent on the application. So it changes from application to application. But for many applications, one of the important distances, okay, is what is called the Jacquard distance or Jacquard similarity. Okay, uh, this is especially useful if your points are like sparse vectors in high dimensional space. Okay, so so how is Jacquard similarity defined? So Jacquard similarity between two sets, okay, is the size of their intersection divided by the size of their union. Okay, so in this particular case, you can think of a point in a high dimensional space, a sparse point in a high dimensional space, as a set. Okay, we will discuss how. Okay, but essentially, if the elements corresponding to 0 are the ones that are not included, and the elements corresponding to non-zero are the ones that are included. Okay, so that is how you compute. And moreover, the non-zero elements, you can just think of them, all of them, as 1. Okay, in that situation, okay, you can think of um, each point in high dimensional space as a set. Okay, and you can think of Jacquard similarity between two sets as their union by intersection. So this has the property, as you can understand, is that this lies between 0 to 1. Okay, the maximum value can be 1 and the minimum value can be 0. The maximum value is 1, is achieved when all the elements of the two sets have the two sets are the same. The two sets are identical. Okay, and then since this is between 0 and 1, you can also define the Jacquard distance, which is 1 minus Jacquard similarity. So remember that uh, in this notion of Jacquard similarity, the more similar the two sets C1 and C2, let's say, are, the more they are close. Okay, Jacquard distance is like uh, the the more similar two sets are, okay, the smaller the distance. So if the two sets are identical, then the distance is 0, because it's 1 minus 1. Okay, so this is the notion of similarity that we are going to use today in the first one. Okay, so here is a small example. So you have 3 points in the intersection and a total of 8 points in the unions. Jacquard similarity is 3 by 8, whereas Jacquard distance is 5 by 8. Okay, now let us look at an application where such a similarity or a distance measure will be useful. Okay, So the goal here of the application is that suppose you are given a large number of documents. Okay, so you're given, let's say, uh, n, which is in millions. Okay, so 10 to the power 6 many documents. Okay, and you have to find near duplicate pairs. That is, you have to find for each document other documents which are similar to this particular document. Okay, so this is a problem. So what are the applications where this problem needs to be solved? Okay, so so one is, for example, mirror websites. Okay, so let's say you are running a web company, something, or a web search company or something. Okay, something like Google, where you are crawling the web. Okay, or you are displaying web search results. Okay, so if you know that a particular web page is a duplicate or a mirror of another web page, okay, then you don't want to index both the web pages separately. You just want to store that the second web page. Okay, so they may be addressed by two different URLs. So you may have URL 1 and URL 2, but both store, let's say, the same content, or partially same content. Okay, or very very similar content, let's say. Okay, then you may want to store URL 1 or URL 2 as a duplicate of URL 1, and at the time of display of search results also, you don't want to show both results because they're the same, so you just want to show one of them. Okay, so this is one application. Okay, you may have millions or actually billions of web pages. Okay, and you want to find out which pair of these are similar. Similarly, you may same thing can happen between news articles, for example. Okay, so many a times one news article is bought by another news website, and with minor changes, the same news article is sometimes presented. Okay, or sometimes the other website is a news aggregator website, and in that case, it may present the same news article published by another. So same problem occurs there also. Okay, now these are the applications. Okay, so what are the problems? Okay, so you see, the so it is not an exact match. Okay, so the first problem is that many small pieces of one document can appear out of order in another one. Okay, so this is one thing. So there is no fixed order, in a web page. So it may be that the order is presented is somewhat different in one web page than in other. Okay, and that too only not all the, so let's say the document is divided into many paragraphs, and not all the paragraphs appear, but many of the paragraphs appear, many small parts of the paragraphs, or some small piece of the documents, many of them, they appear together. Okay, so this is not an exact match. Okay, so this is the first problem. The second problem is that you know so I can say here, uh, inexact match. So you want to also search for inexact match. Okay, so this is the first problem. Okay, the uh, second characteristic of this problem is that you have too many documents to compare all pairs. Okay, so you cannot compare, so you cannot apply a simple algorithm where you compare all pairs. And the third thing is that, uh, you know if you consider all billions of web pages, okay, if you try to store all of them in the memory, so we are now just talking about text. Okay, but there may be also images and all those things. Okay, and then you cannot store the whole document or all the, let's say, millions of documents in the main memory at the same time. Okay, in a RAM at the same time. Okay, so these are the three problems. Now, how do you solve this problem? Okay, or how do you find the near neighbors in the setting that we just described? Okay, so that is sort of a representative problem or an example problem which we need to solve. Okay, so the the technique that we are going to describe today is something like it consists of three essential steps. Okay, so the first step is what is called shingling. Okay, so here we basically convert documents to sets. Okay, second step is called min hashing. Okay, so we basically convert such large sets to short signatures while preserving the pairwise similarity. So we only, calculate short signatures which we can fit into the memory at the same time, and also, roughly the pairwise similarity is preserved. Okay, and then finally we describe a technique called locality sensitive hashing. Okay, which gives us a easy way of focusing on uh, pairs of signatures, which is kind of a proxy for the pairs of documents. Okay, which are likely from similar documents. Okay, so these can be candidate pairs. Okay, so if by taking this technique we can quickly boil down the search to some pairs of documents which are likely to be similar. Okay, then we can perform the entire task in a much more efficient way. So this is our approach. So here is the big picture story. So we have the document. Okay, we are going to perform the shingling operation on the set of documents. Okay, uh, this is like computing shingles for each document is like you can do it one document at a time. So you can do it, you can think of it as a that you can do it in a one pass in a streaming manner. Okay, and after you have done that you have a set of strings of length k that appear in a drop. So we will come to what exactly shingles are. Okay, and then once you have the shingles, okay, we pass the shingles to this min hashing operations, which converts these singles, which again correspond to each of the documents, okay, to signatures. Okay, so these signatures are, let's say, short integer vectors that represent the underlying sets of shingles. Okay, and also reflect their similarities. Okay, so these are the min hash signatures uh, of the shingles for each document. uh, in general you can find min hash signatures for any sets. Okay, uh, so this is what is the min hashing. Okay, and then finally you pass this through to the locality sensitive hashing. Okay, whose job is to find the candidate pairs. Okay, so this finds the signatures of each document. The locality sensitive hashing finds pairs of documents whose signatures we need to test for similarity. Okay, so these are likely to be very simple. Okay, so the first step, which is the shingling. Okay, so what is shingling? So as we described, shingling is the process of converting documents to text to sets. Okay, so how does one convert a document to a set? Okay, so it is really dependent on the application. Okay, so for simple application, let's say you are talking about documents where you have only English text. Okay, so I have given the example of web pages. Suppose you are only talking about English web pages. Okay, you know that all the web pages are in English. Okay, and it's a very high quality text. Okay, then you can just find out the set of words for these documents. Okay, uh, and then each you know so you have a vocabulary of certain number of words. Okay, and now basically your document is represented by the subset of the entire vocabulary, that is the set of the words which appear in that document. Okay? um, Sometimes you can also use set of important words. Okay, so you can have a set of what are called stop words. Okay, which are not so important words like is, as, the, etc., and you can only focus on the important words, and then you can define the document as the set of important words also. Now for example, for the application at least of searching duplicate web pages, these don't work so well. Okay, uh, okay, so the reason is that many a times, so there are two main reasons. One is that many a times you have let's say some web pages, portions of which may be in Chinese or maybe in some other document language, where words may not be so well defined. Okay, uh, so this is one problem. The second problem is, even if it is a English document, there may be errors. Okay, so people may not always put spaces in between words, or people may put extra spaces, and or the data may be represented in a strange manner and in a weird manner, such that in the text you find that there are spaces. Okay, but while rendering the HTML, it may be that your spaces are not there, because maybe the position has shifted or something like that. Okay, so for this application, these kind of approaches are uh, not so important. Okay, also you may need to take ordering of words and so on and so forth. So the this the different way, or the simple way, is to use what are called shingles. Okay, so k shingle or a k gram for a document is a sequence of k tokens. Okay, so in this case, okay, tokens can be, for example, characters. Okay, so you may have characters. Okay, these are like, let's say, if your document is encoded in Unicode, so these are like uh, you know uh, 2-byte characters. Okay, and uh, you have a particular k, let's say k is equal to 5 or 6 or whatever, you can choose that k. Okay, and then basically your shingles are all sequences of all sequences of key characters, okay, appearing one after the other. Okay, so for example, suppose your document is like this: a b c a b. Okay, and your k is 2. Okay, then your set of two shingles, okay, are going to be AB, BC, and CA. So AB is there, BC is there, CA is there, and then again AB. Okay. You can also represent shingles as a bag or a multi-set, where you basically count the last AB. So you have AB twice. So you can have like this. Okay. Uh, but it is more common to use the sets. Now, as you can understand that this, so in order to process, okay, so there may be very long shingles also. Okay, uh, so in order to process it efficiently, one has to somehow come up with compact representations of shingles. So how can one represent or come up with compact representations of shingles? Okay, so a simple solution is to use a hash function. Okay, so here we can just let's say represent each each shingle, okay, by a, let's say, 4 bytes or by a 4-byte integer. 4-byte unsigned, you can interpret this as 4-byte unsigned integers. Okay, and then you just represent a document by the set of hash values of its k shingles. Okay, and the idea here is that two documents could rarely appear to have shingles in common when in fact only the hash values were shared. Okay, so again, our in our running example, so your shingles set of shingles for this document D1 was A, B, B, C, and C, A, and now you have done this mapping of age where you have mapped this AB to 1, BC to 5, okay, and CA to 7. Okay, and you know uh, instead of storing these long shingles, so you will typically have like at least k is equal to 5 or something. Okay, instead of that, now you can just share these compact numbers. Okay, and these are also easy to compare and everything. Okay, so now uh, so consider now that you have a document represented as a set of its k shingles. Okay. Uh, Now, an equivalent way of thinking about it is that now suppose you have a master set of k shingles. Typically, if you have like k shingles of, let's say, let's say like 16 bit numbers, right? So 16 bit, so 2 to the power 16 numbers, right? So you actually have 2 to the power 16 to the power k, this many possible shingles. Okay, so this is now your set of all shingles. Okay, and each unique singles is now one dimension. Okay, and your document is now a fixed length vector. So your document was all this very noisy variable length text, uh, and it need not be just text. There may be URLs, there may be symbols, there may be images, all these things. Okay, but now you have sort of, by this shingling method, you have boiled it down to a 0 1 vector in this 2 to the power 16 to the power k space. Okay, so basically a space where each dimension is a unique shingle. Okay, and whichever shingles are present in a document, that particular element of that dimension is 1. Otherwise, all the shingles which are not present, the corresponding dimension is 0. Okay. Now, it is expected that most documents are very sparse. Okay, because you can imagine that every web page will have only a small fraction of the shingles present. And now, as we have hinted earlier, okay, natural similarity measure between such sparse set of uh, vectors, okay, or sparse. So you can think of it as a set, or you can think of it as vectors in high dimension. Okay. Jacquard similarity is a very natural notion of similarity between such sparse set of vectors. Now, the assumption here is that documents that have lots of shingles is in common, okay, are similar or have similar text. Okay, uh, even if the text appears in different order. Okay, so order is somehow implicitly captured. Okay, so one of the reasons why order is implicitly captured is because you are taking, remember, you are taking a sliding window, so there are a lot of overlapping characters in the shingles, and if you take a large number of characters, if you take a large case, something like 5 or even 10, okay, then you have a lot of overlapping portion, and that makes sure that the order is somehow, some order information at least is maintained in the set of shingles that appear. Okay, uh, so so the idea here is that how, so the question is, how do you pick k? Okay, and the idea here is that you must pick k large enough so that there is some distinctiveness between the documents. So the think about it the other way, that suppose you pick just k is equal to 1. Okay, so then k is equal to 1 means all the English characters. Now all the characters may appear in all the documents. Okay, so then you have a set of 26 shingles, each of which appear in all the documents. Okay, so the similarity between all pairs of documents is 1. Okay, in this shingle space. Okay, but as you take more and more k, okay, you start to see more and more larger and larger sequences. If you take k to be very large, let's say larger than uh, uh, larger than or very close to size of the documents, okay, you may see only one or two single shingles present in each document. Total number of possible shingles is going to be very very large. Okay, and but there you have a, you preserve the order information very very strongly. So that is the caveat of how you choose the. We need to find near duplicate documents. Okay, among let's say 1 million document. Okay, so this is our problem. This is the problem that we discussed. Okay, so we have already boiled down our documents to sets of shingles. We can just represent them as sets of shingles and then compute pairwise similarities, right? Now the problem is, think of how many pairwise similarities you will have to compute. Okay, so here, and 1 million is not a large number. Okay, in a document corpus you will routinely get document corpuses which are this large. You can get much larger document corpuses. Okay, and here the pair is actually ordered n square, so you get about 10 to the power 12. Basically you get ordered 10 to the power 12 many pairs to compare. Okay, now this is difficult because even if you compare 10 to the power 6 documents per second, okay, which is reasonable. You have roughly clock speed of 10 to the power 9, and let's say you take like of the order of 1000 clock cycles to compare each pair of document, which is very very reasonable. Okay, uh, you will be taking 5 days, okay, to go through all pairs. Okay, this is not acceptable because this and 1 million is not a very large document collection. Okay, and of course it's n squared, so it grows very fast. So 10 million, it takes more than a year, so it's already not feasible to do this. Okay, so the question is, how do we you know you know boil it down to a manageable number? Okay, okay, so let us see. Okay, so now we use what is called the min hashing first to convert these large sets to short signatures while preserving similarity. Okay, our notion of similarity, which is the Jaccard similarity. Okay, so as we have discussed, yeah, so in many similarity problems, they can be formalized as as finding subsets that have significant intersection. Okay, and we encode sets using a 0 1 boolean vectors. Okay, uh, and one dimension. So one dimension of this vector corresponds to one element of in the universal set, like in case of shingles, like in the shingle vocabulary or something like that. Okay, and then you can just interpret the set intersection as the bitwise and the set union as the bitwise or. Okay, so just to show an example, like let's say C1 is one document and C2 is another document. Okay, and you can see that the universal set is of size 5, and in C1 the second vector is missing, uh, second element is missing, and C2 second and third elements are missing. So the intersection is 3 and the union is 4, so Jaccard similarity is 3 by 4. So now further, so just for the analysis of the algorithm, we will understand this as sort of a document matrix. You can think of it as a document matrix. This is just for analysis. This is now how we will actually represent the data. Okay, because this is wasteful. So this is only for the understanding purpose. Okay, so what is the document matrix? Okay, so your rows are basically shingles here, or whatever you are using. So your rows are basically your there may be 2 to the power 16 to the power k, something like this. Okay, this many rows are there, and here you have the document. So let's say you have 10 to the power 6 documents. Okay, each column is a document. Okay, so this is what we are saying. So and as you can understand, this matrix is really going to be sparse. So it's going to be very sparse. So some shingles may also never, so some rows may just be all zero, so they may never appear in any of the documents. And yeah, you can also ignore them, but C1 and C2. So here this is C1 and this is C2. Okay, these are the documents. So, and you can see this. So one important thing to notice here probably is that because you are dividing intersection by union, so naturally the shingles which don't appear in both of the documents, they naturally don't count. So you may have any number of shingles, only the shingles which appear in this pair of documents count. Okay, so that is an important property of this Jaccard similarity. Okay, we are not counting all pairs of shingles. Okay, here we are counting only those which are there in the union of pairs of documents. So that is kind of important. Okay, now the next goal, okay, is to find similar columns while compute while computing small signatures. So two things. So here you can see that basically you can think of this fixed size vector for each document, this a column here, okay, as a signature, but this signature is very large. Okay, this so we want to find a more compact signature uh, while preserving the similarity. So after this, we are just going to forget about this document and we are going to just look at this signature. Let us see how we compute the signature of each column. Okay, so here the key idea is that we hash. So here the word hash is kind of in quotes. Okay, so we will actually use what is called a min hash. We will see what this is. Okay, so we hash each column into a small signature which we call h of c. Okay, so each column, remember, is a 0 1 bit vector. Okay, okay, but this is a large 0 1 bit vector. It is at least a high dimensional 0 1 bit vector. Okay, uh, so uh, so c is a high dimensional vector. We want to compute h of c, which is a very low dimensional vector. Okay, it may not be a bit vector, but it's a low dimensional vector. Okay, such that this similarity sim between C1 and C2, the original high dimensional vectors, can be computed using the signatures h of C1 and h of C2. So how does this work? Okay, so more importantly, okay, so here now note that this, when I say this hash function h, we are going to have a randomized hash function here, just like our other, so we have seen in the previous applications also. Okay, now how is this signature, so in what sense must this signature h of c1 and h of c2 preserve the similarity sim of c1 comma c2? Okay, now there the notion is that if sim of c1 comma c2 is high, okay, then the probability that h of c1 is equal to h of c2 is going to be high. And if sim between c1 and c2 is low, then uh, with high probability h of c1 is not going to be equal to h of c2. Okay, so this is the sense in which we are going to say that the hash signature, okay, preserves the similarity. Okay, so in other words, suppose now our hashing function is just giving the ID of a bucket. Okay, it's a random hashing function, but each instance of a hashing function, when you feed it vector 0 1 bit vector or something, okay, it comes up with one bucket ID, so maybe one integer. Okay, so basically it hashes the documents into buckets. Okay, and then in the above definition what we see is that most pairs of near duplicate docs will hash into the same bucket. So this is something that we will use later, okay, in locality sensitive hashing. But this is the idea of computing min hash. Okay, so we have seen this. Okay, uh, okay. Now the question is, can we do this for all similarities? Okay, so here we are writing sim of c1 comma c2. Okay, but what we are really using is the Jaccard similarity. Okay, so sim of c1 comma c2 is the Jaccard similarity. Okay, so the hash function which has this property, okay, this property that if sim of c1 comma c2 is high, then with high probability h of c1 is going to be equal to h of c2. Okay, that hash function is called the min hash function. Okay, for Jaccard similarity, and for any arbitrary similarity, you may not also have such an appropriate hash function. We will see why or how. Okay, okay. So what is the min hash function? Okay, so the min hash function is really very simple. Okay, so now consider our document matrix that we discussed earlier, where each row is a shingle. Okay, now consider a random permutation pi of the rows of this matrix. Okay, a random permutation pi of the rows of this matrix. Okay, and now define a hash function h pi of c as the index of the first uh, row, okay, in the permuted order, which has a value 1. Okay, so for every column, so we will see an examples, but you can understand that for every column, okay, uh, you can calculate, let's say, you have some original set of indices starting from 1 to, let's say, something like whatever is the number of shingles. Okay, so let's call this n. Okay, now we do a permutation pi of this. Okay, so we do a permutation pi of this. Okay, now in the revised permutation, okay, something will come here. Okay, so let's say it is something like 432 or something. Okay, and now we start from the top and we find out the index for which, let's say, 2 is the first index that we find. 4 and 3 both had 0. This is the first index which we find, where for a given column, you had a 1. Okay, then we say that for that particular column C and for that particular permutation pi, okay, the h pi of C is going to be this 2. That is the minimum of the permuted sequence, such that you have a 1 in the original listing. Okay, and in practice we can use several hashing function to so remember, this is a random hash function because your permutation is random. So depending on what permutation of the rows you do, you will have different signatures for each column. Okay, okay, so let us see an example. Okay, so remember that this is our document matrix. So you have a total of 7 rows. 1 2 3 4 5 6 7. You have a total of 7 rows. Okay, and you have 4 documents. Okay, so 7 shingles, 4 documents, and this is your basically your document matrix. Now this is the first permutation. Okay, so uh, 2 3 7 6 1 5 4. Okay, you are permuting the rows of the column. Okay, now what are going to be the corresponding shingles? Okay, so the corresponding min hash signature. Okay, so the corresponding min hash signature is going to be 2121. So how do you compute the corresponding min hash signature? Okay, so you first see 2. Okay, so the first in the first basically row in the permutation is 2. Okay, so in 2 you see that the first document and the last document have the, okay, because so you put 1 and 1 here. Okay, this one becomes 2. Okay, and yeah, because for 3 this one is 1 and this one is 1, but the first one here has already come. Okay, then comes 7. So let us see 7. Yeah, so 7, this one is 1, so this becomes 3. Okay, so this is the min hash signature. Okay, okay, Now let us see 4. Okay, so 4 is 1 and 1 here, so this is 1 and 1. Okay, next is 2. Okay, so 1 and 1 here, so this one becomes uh, uh, 2, so 2 here is 2. Okay, and then 1. Okay, that's yeah. Okay, 1 3 6 7, so this one should be something like 6. Okay, uh, uh, sorry, I think I'm doing a miscalculation. 4 4 is 1 and 1. Okay, so here we put 1 and 1. 2 is 2, so we put 2 here. 1 is this one. Okay, so we have to put 3 here. Right, this is 1, and this is the first time it is becoming 1. Okay, yeah. Mm, and then finally, so 3 again, so yeah, it's going to be 1 and 1. 4 is going to be same 1 and 1, so no change. 7 is going to be 1 and 1 here, so 3 and 3. Okay, so actually this is the min hash signatures. Okay, uh, okay, so I think the idea is clear. Okay, now the question is that why is okay, yeah, so uh, so now the claim is that this particular min hash function, okay, has the property that probability for, so you take any random permutation pi, okay, the probability of h pi of c1 being equal to h pi of c2 is equal to similarity between c1 and c2. So here similarity is the Jaccard similarity, and the question is why. Okay, so suppose X is a document represented by like C1 or C2, okay, which is a set of shingles. Okay, and Y is a shingle which is present in a document. Okay, now what is the chance that pi of Y, okay, that is the permuted position of the shingle Y which is present in the document X, okay, will land up as the minimum element in X. Okay, now my claim is that this is just 1 by the number of shingles in X. Why is this? Because whatever shingles you have, okay, uh, you can have uh, so you can just ignore the zero entries basically. Okay, so your total set of shingles may be very high, but you only need to look at shingles which are present in this document X. Okay, so there are mod of X many of them. Okay, so you consider this sort of bucket, okay, where you have uh, this mod of x many positions, okay, and y is one particular single. Now your y was somewhere, so you are permuting y's. So what is the chance that y will be the first guy? Okay, and the chance of that happening is the same. It's because it's a random permutation. uh, the chance of that happening is the chance that this this shingle y will end up in the first position among all the positions that have, and that chance is basically 1 by mod of x. Okay, so okay, so now uh, consider your document, okay, which is formed by the union of two documents C1 and C2. Okay, so these are the two documents, let's say C1 and C2, and consider the documents which are formed by union of two documents. Okay, uh, okay, then your pi of y is minimum of pi of C1 if y belongs to C1, or minimum of pi of C2 if y belongs to C2. Okay, so whichever of these documents the minimum belongs to, okay, uh, it will be that one. Okay, and so the probability that this pi of y is equal to minimum of pi of C1 and minimum of pi of C2. Okay, so y is present in both pi of C1 and pi of C2. Okay, is the probability of uh, yeah. So the probability that y is present in both. Okay, now what is the probability that minimum of pi of C1 is equal to minimum of pi of C2? Okay, so this is just you can think of it as uh, this is just intersection between C1 and C2 divided by union between C1 and C2. Okay, which is the similarity. Okay, hence the claim. Okay, so why is the last case true? Okay, so in order to see this, uh, so consider, so you look at this picture. Okay, so you have C1 here and you have C2 here. Okay, column 1 and column 2, and there are, so for the pair C1 and C2 you can have these four types of rows. Okay, type A rows, type B rows, type C rows, and type D rows. Okay, okay, and there are many of these rows. Okay, now the first thing to consider is that type D rows are immaterial, which consist of shingles which are not present either in C1 or in C2. Okay, so you can insert any of them anywhere. It doesn't really change the mean hash value. Okay, now in terms of Jacquard similarity, what is the Jacquard similarity? Jacquard similarity is basically uh, type number of type A rows, which we are denoting by small a, divided by the total number of all the rows, which is small a plus small b plus small c. So number of small a type rows plus number of small b type rows plus number of small c type rows. Okay. Now, what is the Jacquard similarity? It is a by a plus b plus c. Okay. Now, what is the probability that uh, your your uh, hash function of C1 will be equal to hash function of C2. Okay, you recall that this happens only when uh, you know a particular like a particular row comes to this comes to top basically. So there is going to be a permutation and then a particular row comes to top. Okay, now in this case only if type A row comes to top among A, B and C, D type rows anyway don't matter, will this happen. If any other type of row comes to the top position, okay, this will not happen. Okay, so what is the chance of that happening? Yeah, so the chance of that happening again is A. Okay, so total number of rows here are A plus B plus C. Okay, and out of which if only type A rows comes to top, okay, this is what will happen. So and this is what is counted by the min hash. Okay, so the probability that uh, min hash signature of C1 matches min hash signature of C2 is also A by A plus B plus C. Hence the two are same. Okay, uh, I hope, because this permutation is a random permutation. Okay, so this is for a single random permutation pi. Okay, now you can generate many such random permutations independently. Okay, so we can generalize this to multiple hash functions. Okay, and then we can say that the similarity, so we are generating many of these pi's independently. Okay, then similarity that two of the uh, you know two of the hash signatures is same, or rather the similarity between two of the hash signatures is the fraction of hash functions on which they agree. Okay, and this is because of this probability definition basically. Okay, so yeah, so this matrix is not correct, but let us go with this matrix. So so here uh, you can just see the actual similarity. If you see the column to column similarity here, okay, so this is the column to column similarity. So between 1 and 3 is 0.75, between 2 and 4, so this is column, okay, let me say column 1 and column 3 is 0.75, 2 and 4 is also 0.75, and 1 and 2 and 3 and 4 are 0. So there are no common symbols between these. Okay, and this is what comes. When you consider the signature, the similarity comes out to be here 0.67, here 1, here 0, and 0. Okay? So yeah. Okay, so you have approximated this large matrix. So in this case, this was 7 size, but this can be very large number of rows to this manageable number of integers while preserving the similarity. Okay, so for example, you can understand that the min hash signature of the first column here is 221. Okay, yeah, okay, so yeah, so let's say suppose you take 100 such min hash signatures. Okay, uh, and then each signature you represent by 4 bytes or something like this. Okay, then you have basically 400 bytes, right? uh, okay, and yeah, so that is much more manageable than let's say if you were to Yeah, if you were to store the entire 0 1 matrix even in a sparse format, then that may be very large. Okay, now uh, the question but here is that, you know, how do you efficiently compute the min hash signature? Yeah, so how do you efficiently compute the min hash signature? Okay, so clearly if you keep permuting uh, you know the rows even once, it's going to be prohibitive. Okay, right? Because you have a large number of rows, and most likely most of the shingles are not going to be present. Okay, so how do you do this? Okay, and the answer here is that you have to pick. So what you do is you initialize. Okay, so first of all you pick k random hash functions. Okay, uh, okay, so the idea is that you generate the permutation, okay, using a a random hash function. Okay, okay. So now you initialize the signature matrix, which is sig c of I. So cth column and ith row here, okay, to infinity. Okay, so you think first that all of them, uh, all the min hash signatures are infinite. Okay, now for you scan the rows looking for ones. Okay, so what do? You basically hmm, so so you know the union of ki. Okay, so you have the hash functions ki. Okay, so you have the hash functions ki. Okay, and you know the ki's which are present in c1 and c2. Actually c1 till c, let's say m. So let's say you have m documents. Okay, m docs. Okay, so you know all the shingles which are present in all the documents. So this is so you have to make one pass to find this out. So you have all the ais. Okay, and you have all the hash functions. Okay, now you just go over the shingles. Okay, so uh, so it's something like so you do one pass over the shingles. Okay, or in this case rows. Okay, so for each row j which is present in at least one of the documents. Okay, you check if you know for each ki if the kij that you are getting, okay, uh, that is less than your yeah, so your sig c of I. Okay, so initially everything is infinity. Okay, but you may also find um, signatures of you may also find so you may scan them in a different order, right? Okay, so your KIs need not always be increasing. Okay, yeah, so if your ki of j uh, is less than, okay, the current stored signature of the ith you know, of the ith row of uh, column C, then you set this sig of C comma I to ki of j. Okay, so in this case, basically in two passes, so you need kind of like two passes. Okay, so one pass to actually you don't even need two passes, you just need one pass through the data. Okay, uh, because you can sort of, you can compute the index, you can just uh, have a permutation function, okay, which will compute the index of uh, each shingle. Okay, and yeah, you know how to choose random permutation function, so I'm not going to go into detail of that. Okay, but you basically can compute then in one pass itself, okay, all the hash signatures. Okay, and then yeah, I think, okay, so now that you have got the min hash signatures efficiently for all the documents, okay, how do you efficiently compute the locality sensitive hash function? And the answer is here, rather answer here is to use what is called the locality sensitive hashing. Okay, so the goal of locality sensitive hashing is to find documents with Jacquard similarity at least S, okay, for some similarity threshold, let's say S is equal to zero point 0.8. Okay, so you want to find documents or pairs of documents rather in this case where the similarity is at least 80%. Okay, so that is what is called a candidate pair. Okay, and basically we want to generate a function f x comma y where x is one column and y is another column, x is one document and y is another document, and then uh, we want to find the candidate pair. Now in our case, basically each column, you remember, is represented by a min hash signature. Okay, so this is represented by a vector of integers, okay, one corresponding to each permutation of the rows of the document matrix. Okay, so this is the M matrix. Okay, this is defined as the M matrix here. Okay, yeah, so then as you can understand, so the let's say you have this ith entries, okay, or ith rows of the M matrix. Okay, so then you know, your between the columns x and y, or rather the columns x and y which correspond to documents x and y, are a candidate pair if, okay, at least s fraction of uh, this mix and miy. Okay, I varies for from 1 to k, let's say. So if you have taken k min hash functions, okay, then I is equal to 1 to k. Okay, so if s fraction of these i's are equal, okay, so that is mix is equal to miy for at least s fraction of all the i's. Okay, okay, so how do we do this? Okay, so this idea, so this is kind of done, right? So how, see, so these, remember, these hash signatures are integers. Okay, so we can think of each integer in the min hash signature as the bucket ID. Okay, and then uh, you know there are all these buckets. Okay, and then each document or each column gets mapped to its corresponding bucket. Okay, using the min hash signature. Okay? The min hash signature or the min hash index or the integer that you have computed. So you have computed multiple of them, but for the time being just consider one min hash signature. Okay, that will give the ID of the bucket. Okay, so if you have like one min hash signature, so you remember there were 4 documents. Okay, C1, C2, C3 and C4, and it was something like 2121. Okay, so this 2 is the ID for C1, this one is the ID for C2, this 2 is the ID for C3, and this one is the ID for C4. So there are like 2 buckets here. C1 and C2 fall into this bucket, and C3 and C4 fall into the second bucket. Now, what are the candidate pairs? Candidate pairs are just documents which fall into the same bucket. Okay, why is this? Because remember the chance that they fall into the same bucket is sorry, no, it's not straightforward like that. Okay, but it is true that the chance that they fall into the same bucket is uh, you know their similarity basically. So the probability that they fall into the same bucket is their similarity. Okay, so how do you solve this? Okay, uh, so the way this is done in locality sensitive hashing is that you take the min hash signature matrix now. Okay, so min hash signature matrix, remember the rows are now the bucket IDs. Okay, and the columns are documents as usual. Okay, and now you do what is called the banding trick. So what is the banding trick? The banding trick is that suppose you have a total of b times r many rows. Okay, this is the total number of permutations that you have computed, or total number of hash functions that you have used. Okay, if this is the case, you sort of split this into b bands. Okay, you split this into b bands. Okay, uh, each band has r many rows. Okay, so in other words, this entire min hash signature of b into r size, okay, you are splitting into b different min hash signatures, each of size r. Okay, this is for each column you are doing. Okay, and now what you are going to do, you are going to take each of these representations. Okay, so you are going to take this particular min hash signature which is there in each band. Okay, and you are going to construct a bucket using r of these signatures. Okay, in other words, earlier we were saying that, here we were saying that if one signature matches, you put them in the same bucket. Here we are saying that if r signature matches, okay, then you put them into the same bucket, and do this for all the b bands. Okay, so here this is what we are doing. We are saying that uh, you know if uh, for 2 columns, okay, there are basically b bands, so there are b buckets this column will be mapped to. Okay, each bucket is constructed by a signature of size r, so r integers define this bucket. Okay, now so two buckets match only if all r of the integers in those buckets match. Okay. Now, pair of uh, columns, okay, uh, are candidate if they match, or at least one of the bands of their min hash. So they have, remember, B bands. Okay, so at least one of the bands, the min hash signature corresponding to the at least one of the match, they match. That is, they fall into the same bucket. Okay, so this is pictorially represented. So you can think like that. There are all these columns. Okay, and each column is getting mapped to one of the buckets. Okay, so and then you see that at least there is a match here, there is a match here, and there is a match here. Okay, uh, so this and this, so these two are one candidate pair because in at least one of the buckets they have matched. Okay, these two are another candidate pair. Okay, and these two are another candidate. So this is how you get the candidate pairs in locality sensitive hashing. Okay, yeah, okay. So yeah, so we assume that there are enough buckets, because essentially what we will see is that this matching of buckets is essentially comparing, uh, yeah. So you just have to compare all the integers. Okay, so we are going to assume that uh, 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 you know these min hash signature, or rather this kind of banding tree. Okay, the with the rows within the same band, okay, they get mapped to the same bucket only if they are identical. Okay, uh, okay, okay, this is of course only to simplify the analysis. Okay, we will do the analysis under these circumstances, but even if there is some amount of overlap, even though they are not identical, they are still getting mapped to the same bucket. Okay, the algorithm will still work, but the analysis may become a little bit more difficult. Okay, okay. So now, just to give you an idea, so let's say there are 100,000 documents. Okay, and you are using min hash signature of 100 integers, so total of 100 rows, and you have done so this, you can think, uh, is about 40 megabytes of data. So this is not too much data. Okay, so you have stored uh, and this is also linear in the number of documents. Okay, so you have a certain number of rows, something like 100 rows. Now if you increase the document number of documents a lot, it's not going to increase, the space is not going to increase quadratically. Okay, so yeah, now you are having, let's say, 100 rows, and you do the banding trick and you choose 20 bands, each of size 5 rows. Okay, or 5 integers per band. Okay, so your bucket here is going to be defined using 5 integers. Okay, then uh, what you get here is yeah, and now you are given that you find pairs of documents that are at least 80% similar. Okay, now what is the idea here? Okay, so so suppose now assume that uh, the similarity between two documents is zero point 0.8. Okay, okay, now this as the high, so our concern here is that there may be a false negative. False negative means they are actually 80% similar, but they are not falling into the same bucket. Okay, and this will happen when the actual similarity is just borderline 0.8. Okay, and still they are not falling into the same bucket. Okay, so what is the chance of that happening? Okay, and you can understand that their actual similarity, okay, s is zero point 0.8. Okay, so the chance that your for each band, okay, each band of 5 integers, okay, the chance that they are going to be identical is zero point 0.8 to the power 5, because each one has to match, and the chance of each matching, each min hash signature matching, as we have established, is zero point 0.8. It is the signature matching is same as the probability between the yeah between the actual documents. Okay, so uh, okay, so the probability that in any band they are going to be identical is zero point 0.8 to the power 5, which comes out to be roughly 0.328. Okay, now what is the probability that C1 and C2 are not similar, okay, in all of the 20 bands? Okay, so in any band the probability that they are not similar is 1 minus 0.328, and that has to happen for all the 20 bands, so this to the power 20. Okay, and this turns out to be this 0.00035. Okay, so this is about 1 by 3000. Okay, or there is a like you can say 99.965% chance that you will find with this 100 uh, hash functions split into 20 bands of 5 rows each. There's 99.6% chance, 99.96% chance that you will uh, find similar the 80% similar items. Okay, only there's a like there is this much chance, basically something like 0.035% chance that there will be a false negative. Okay, now let us consider the other case. Okay, suppose this is the same sketch. Okay, suppose now that C1 and C2 are uh, having an actual similarity of zero point 0.3. Okay, what is the chance that uh, you know your your similarity, uh, I mean they will come up as uh, candidate pairs? Okay, now yeah, so uh, so we want them to hash to no common buckets. Okay, now again, what is the we do the same analysis. So what is the chance that they are identical? Now this is 0.3 to the power 5. Okay, which is 0.000243. Okay, now what is the probability that they are identical in at least one of the 20 bands? Okay, this is 1 minus this thing to the power 20. Okay, this is the probability that they are not identical in any of the 20 bands. Okay, so the probability inside is that they are not identical, or they are not they are not colliding, or they are not falling into the same bucket in any of the 20 bands. Okay, and that to the power 20, and 1 minus that is that at least in one of the 20 bands, they're coming out to be identical. And this comes out to be about 4.7%. So we'll have for of the document pairs which have 30% similarity, okay, we will have a 4.7% chance of false positives. Okay, so you can see that you may have to look at about 5% of false positives. Of course, when you look at these pairs of documents, okay, you you will know the correct answer, okay, but you will have to evaluate them. Okay, so this is the key idea here, that false positive doesn't mean that you actually report them as similar, but you have to evaluate them nonetheless. Okay, so but remember, even 5% is high here, because if you recall, so if you have 1 million uh, documents, okay, you have actually 10 to the power 11 many pairs of comparisons to perform. Okay, now suppose a very small number of them are similar, okay, but let's say all pairs of them are at least 30% similar, okay, but I want 80% similarity, okay, still I have to consider about 5% of all pairs, okay, in order to, I have to compute them, I have to compute their similarity, because they are now candidate pairs. Okay, so yeah, so that is the idea. Okay, yeah, now the thing to understand here is that this LSH, okay, so you, first of all, so the question is, how many min hashes do you use, or what is the size of min hash signature that you use? Now here, of course, this is the number of total number of rows which we have taken to be 100, okay, in our case. Okay, of course, this depends on how much memory you have. Okay, so you know how much space each min hash signature is going to take. Okay, and you know how many documents you have. Okay, so you can sort of calculate that based on total amount of memory that you have, how many number of rows you can have. Okay, now the trade-off here is, what do you choose, B to B, and what do you choose, R to B? Okay, now think about it. Okay, if your B, or your number of bands here, okay, yeah, so if your number of bands is more, okay, then you have basically R as less, okay, because your B times R is now fixed. Okay, so you have a fixed B times R, okay, is equal to, let's say, some M or something, or let's put it, I think we have already taken, so let's put this as something like L or something. Okay, so B times R is L, and this is fixed. So if you choose higher B, okay, you get more candidate pairs, okay, because between the bands you are doing an ORing. Remember, it has to be, they have to be in any, at least one of the bands. So even if in one of the bands they are similar, they are a candidate pair. Okay, so if you have more bands, you have less R, so you are basically selecting more candidate pairs, which means you are having more false positive, and uh, but you are having less false negatives. Okay, yeah, whereas uh, if you choose your R to be more, so you have to process many more candidate pairs. Okay, whereas if you choose R to be more, you are doing a stricter match, because now you are matching like are many of the signatures, and the probability of matching signatures, okay, even if you recall here the calculation that we did, yeah, so the probability of anything, so even if this is like 0.99, if your R is very high, it's going to come down. So there will always be a false negative, okay, because the probability is not 100%. So there is not a if there is not a 100% match, then there is a small chance that a random permutation may not match the two, okay, and in that case there's a chance that even though their actual similarity is within the threshold, you may end up being marking them as negative for that particular band, okay. Yeah, so if you increase R more, you basically increase the number of false negatives, okay. Okay, so now what would you want? Okay, you would want like a curve something like this. Okay, so you would want a curve where suppose t in the on the x-axis is your actual similarity between the documents. Okay, and your y-axis is basically uh, the probability that they may be declared as candidate pairs. Okay, and suppose you have a similarity threshold, say S. Okay, so what you want is ideally you want a curve something like this where for all the pairs of documents which are falling on the left side of the threshold S, okay, the probability of them being candidate pair or them sharing a bucket should be 0, and then suddenly it should become 1 at the threshold. Okay, so this is our this thing. Now yeah, so now the thing is, if you use just one band and one row, so if you just use one hash function, your curve looks like this. Okay, because your probability of sharing a bucket is same as the similarity. That is what is the property of the min hash function. Okay, so if you use a min hash function, your curve looks like this. Okay, okay, now we have done this calculation already, so let us formally do this. So suppose you have a pair of columns documents which have actual similarity of t. Okay, this t is between 0 and 1. Okay, and you pick any band with r rows. Okay, the probability that all rows in the band are equal is t to the power r. Okay, now you say that with 1 minus t to the power r probability, some band is unequal, so they don't fall into the same bucket. Okay, now there are b band, so probability that no band is identical is 1 minus t to the power r whole to the power b. Okay, so 1 minus t to the power whole to the power b, this is the expression for uh, the probability that at least one band is identical, that is that C1 and C2 are declared as a candidate pair. Okay, now the curve of that particular plot looks something like this. Okay, and basically yeah, so yeah, so so here this should be t, basically this should be t. Okay, okay, and we have done this calculation, so I'm not going to repeat this calculation, but the curve looks like this. So it comes to here, and then at a value s, okay, it makes a steep jump. So this is the property of this curve. Okay, so as a function of t, okay, at some value s here, it makes a steep jump, and then again it goes straight. So if you plot a curve like this, you'll see that it mostly for positive values of r and b, it behaves like this. Okay, for most positive values. So there are some weird values where it will just behave like this, okay, but we let us not consider the weird values now. Okay? uh, Now the question is, what is the value at which this jump happens? Okay, and this you can find out, okay, by sort of what is the characteristic of this jump point. So the characteristic is that the slope of this curve is very high. Okay, so the derivative uh, of the derivative is maximized in some sense. So the derivative gives the slope, and the slope is maximum. So over all other points, the slope is much smaller. So here for this portion, the slope is smaller. Then the slope suddenly starts increasing here. Okay, uh, and then the slope becomes very high, and then again the slope decreases. So if you see here in this axis, okay, so let me just draw this for you. Okay, so in this x-axis, if I see the plot of how the derivative of this will look, okay, so the derivative will look something like this. So slope will increase and then keep decreasing. So you want to find this point, okay, and this point is basically where the derivative is maximum, okay. And so if we differentiate the derivative of this, let's just take the double derivative and equate to 0, we will see that the value of s comes out to be roughly 1 by b to the power 1 by r, okay, for this value. So basically, if you are given a similarity uh, threshold s, okay, you can sort of design b and r such that this holds. Okay, so this is just some calculations to show that indeed the shape is like that. So initially you can see that it increases slowly, and then there's a sudden jump, and then again it sort of becomes stable. Okay, and now yeah, so you basically yeah, so your blue area is so I don't know, this is coming out as red for me. So this area is your false negative. So this is on the correct side of the threshold, but you are still predicting this as, with certain probability like 0.7 or 0.8% probability, you are predicting this as positive. For, you are not, you're predict, otherwise you're predicting it as negative. And similarly, this area is false positive, okay, where this is on this side of the threshold, on left side of the threshold, but you're sort of, with some low probability, you are calling this positive. Okay, so this is the locality sensitive hashing trick. Okay, yeah, so you can just now tune your MB and R to get almost all pairs with similar signature, but also you have to eliminate most pairs. Okay, so if, like we mentioned, that if you choose B to be too high, then you are not eliminating enough number of pairs. Okay, so you are getting many pairs. If you choose B to be too low, you may not be getting enough number of pairs. So in practice, actually what happens is, when you set up a LSH scheme with a certain B and a R, okay, okay, you can initially choose this B to be very low and R to be very high, and then you can gradually increase B, okay, because once you increase, if you choose B to be very high, you may get many candidate pairs which you may not be able to process. Okay, so what you want is, so suppose you, so many a times you are interested choosing only a certain number of uh, you know most uh, closest candidate pairs. Okay, so you can either choose based on threshold, but many a times you are also choosing based on just a rank. Okay, so let's say you can process something like only the uh, top 1 billion similar pairs. Okay, 10 to the power 9 similar pairs. Okay, that is the maximum you can process. So if you have that information, then you can start with b small. Okay, and increase b till you get about 1 billion candidate pairs. Okay, or maybe you get a little bit more than 1 billion candidate pairs, and then you choose the ones which are closest among them. Okay, yeah, so and also remember that now you can also check to see if the candidate pairs have the same signature or not. So many times, because of this mapping to the bucket, many times even though they don't have a similar signature, they may get mapped to they may get mapped to know, same bucket, but you can choose uh, you can just check if they really have a similar signature or not. Okay, this is just to sort of reduce the randomness due to the mapping function. Okay, or due to the basically the LSH scheme, because LSH also randomly splits between bands and rows. Okay, uh, and then you can also go through the data to find the actual similarity which we discussed. Okay, yeah, so just to summarize, there are three steps: shingling, min hashing, and locality sensitive hashing. So shingling is for finding an appropriate representation which is in terms of sets. You may call it sets, or you may call it shingles, whatever, but documents are represented in terms of sets of k shingles. Okay, and then you are using this min hash function to generate a min hash signature which will fit into the memory. This is because the number of shingles in many actual practical application can be very large to fit into memory, fit the entire matrix, document matrix into memory. Okay, and then also they give you the bucket ID. So the min hash function also gives you the bucket ID, and then you use the locality sensitive hashing trick, which is the banding trick, to actually find the candidate pairs which are similar. Okay, and this is taken again from modern massive data sets. Yeah, and also there's the survey paper, or there's the sort of so Andoni many people uh, approach LSH differently, but this survey paper 2008 CACM survey paper by Andoni is also a good resource for learning LSH.